What if everything we think we know about how the universe works is just wrong? Not a little wrong. Fundamentally, broken at the core wrong. Because right now, astronomers have two totally different answers for how fast the universe is expanding, and they can't both be right. For years, scientists hoped it was just a measurement error, bad data from old telescopes. So they pointed the most powerful telescope ever built at the same stars, and it confirmed the original numbers. So the tools are fine, which means physics itself has a problem nobody can solve yet. So here's the thing that keeps cosmologists up at night. We have two completely independent ways to measure how fast the universe is expanding, and they get totally different answers. And neither team can find a mistake in their own work. Let's get started with the basics. The universe has been expanding since the Big Bang, and the rate of that expansion gets captured in a single number called the Hubble constant. That number tells you how fast a galaxy is moving away from us based on its distance. Get that number right, and you can work backward to figure out how old the universe is, how it grew, and where it's headed. It's kind of the whole ballgame for cosmology. So one way to measure it is to look backward in time, way back, to something called the cosmic microwave background. That's basically the leftover glow from the early universe, light that's been traveling since about 380,000 years after the Big Bang. A satellite called Planck spent years mapping that ancient light in incredible detail. Then scientists took that data and plugged it into the standard model of cosmology, the set of equations we use to describe how the universe behaves, and calculated what the Hubble constant should be today. That method gives you roughly 67 kilometers per second per megaparsec, which means for every megaparsec of distance, that's about 3.26 million light years. A galaxy is flying away from us 67 kilometers faster. The other method is more direct. Instead of looking at ancient light and calculating forward, astronomers go out and actually measure distances to real galaxies right now. And to do that, they use something called the cosmic distance ladder, which is basically a chain of overlapping measurement techniques that lets you build up from nearby distances to really far ones. The key rung on that ladder is a type of star called a Cepheid variable. Cepheids pulse. They brighten and dim in a very regular cycle, and the speed of that pulsing is directly tied to how intrinsically bright the star is. So if you measure how fast a Cepheid is pulsing and compare that to how bright it looks from Earth, you can calculate exactly how far away it is. When you use Cepheids to anchor your distance scale and then measure how fast galaxies are moving away, you get around 73 kilometers per second per megaparsec. So that's 67 from one method and 73 from the other, a gap of about 10%. And in cosmology, 10% is not a rounding error. It's enormous. For a while, most people assumed there had to be a calibration problem somewhere in the distance ladder. Maybe the Cepheid measurements had some kind of systematic error baked into them. Crowded star fields making it hard to isolate individual stars, or dust between us and the galaxy messing with the light. The thinking was, once someone finds and fixes that error, the two numbers will just snap together. But here's what actually happened. Both teams kept refining their data. Independent groups ran their own measurements using totally different approaches. And the gap didn't close. It actually got more statistically significant over time. The Hubble Tension, that's the name this disagreement goes by, sits at around 5 sigma, which is the threshold physicists use to call something a confirmed, real result and not just noise. So the early universe measurement and the late universe measurement are telling two different stories about the same universe, and JWST got sent in to figure out why. So when JWST came online, astronomers had a very specific hope. They wanted it to find a flaw in the Hubble Space Telescope's Cepheid measurements, because that would mean the whole tension was just a data problem and not a real crack in physics. The main suspect was something called crowding. Hubble's resolution, while genuinely impressive for its era, isn't sharp enough to cleanly separate individual stars in dense, distant galaxies. So when Hubble locked onto a Cepheid in a packed star field, it might actually be capturing the blended light of several stars sitting close together. That blending would throw off the brightness reading, and a wrong brightness reading means a wrong distance calculation. It's a small error at each step, but those errors stack up as you climb the distance ladder. And if that crowding error was consistent across many galaxies, it would systematically push the distance ladder's Hubble constant too high. That would explain the whole gap: 67 from the CMB method, 73 from the distance ladder. Just an artifact of Hubble not being able to see clearly enough. It was a clean explanation. Testable, specific, and very fixable. JWST was built to run exactly that test. Its mirror is almost 3 times the diameter of Hubble's, and it observes an infrared light, which punches through dust clouds way better than visible light does. So JWST can look at the exact same Cepheid stars in the exact same galaxies and actually pull apart individual stars that Hubble could only see as a smeared blob. The team that did this work is called SH0ES, led by Nobel laureate Adam Rees, who has been running distance ladder measurements for years. They used JWST to go back and re-examine Cepheids in several critical galaxies. One of the most important was NGC 4258, a galaxy that has water masers near its center. Water masers are basically natural microwave emitters, and because of how they move around the galaxy's core, you can calculate the distance to NGC 4258 using pure geometry, no distance ladder required. That makes it a perfect anchor point to check whether the Cepheid distances are actually correct. So JWST looked, and it did find crowding in the Hubble data. Some of the Cepheids Hubble measured were getting a little extra light blended in from neighboring stars. That part of the original concern was right. But when the team corrected for it, the distances barely shifted. We're talking about a change so small it didn't meaningfully move the final Hubble constant number. It stayed right around 73. JWST confirmed the distance ladder measurements rather than undermining them. That's the result nobody was rooting for. Better data, sharper images, a more powerful telescope, and the tension didn't budge. The tools weren't broken. The measurements were solid, which means the disagreement between 67 and 73 is a real physical problem, not a data cleanup issue. So now physicists are left staring at 2 confirmed, reliable measurements that can't both be correct under our current model of the universe. Some researchers think there might be a new form of dark energy that didn't always behave the way it does now. Others are looking at the possibility of an unknown particle active in the early universe that skewed the CMB predictions. Some are even asking whether the speed of light has always been constant throughout cosmic history. None of those ideas have enough evidence behind them yet to call any of them the answer. So here's where things actually stand. JWST didn't solve the Hubble tension. It just ruled out the easiest explanation. The measurements are confirmed. The disagreement is real. And the standard model of cosmology, the framework physicists have used for decades to explain basically everything, has a crack in it that nobody knows how to fix yet. If that feels unsettling, good. That's what real science looks like when it's working at the edges of what we actually know. Drop a comment with what you think is causing the tension, because we might do a whole video on those theories. Thank you for watching.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.